Last year, in 2023, the FDA granted accelerated approval for a new drug called Tofersen for a rare form of genetic ALS. This is obviously huge for the ALS community and comes on a wave of ALS related drug approvals, but it has even wider implications in the world of drug development. See, this drug was approved not necessarily because of its efficacy or ability to treat disease, but because of its strong evidence that it changed a few certain molecules in the blood. The main one, called neurofilament light, or NfL, has been making headlines in the biotech world, and today I'm going to talk about why. We'll go over how it was used to grant accelerated approval and what it means for other neurodegenerative diseases. Stick around. So first, let's talk about biomarkers. What is a biomarker? Well, biomarker is sort of a grand sweeping term to describe anything that can be used to quantify a disease. In the FDA's own words, biomarkers are characteristics that are objectively measured as indicators of health, disease, or response to an exposure or intervention, including therapeutic interventions. This is pretty vague and honestly quite wordy, so let's break it down. The first part, characteristic that we can objectively measure, means that this biomarker is something we can physically test for, and it's usually molecular. A very common example of this is in a blood test you might do at a doctor's office. A biomarker would be any molecule in that blood test, so things like red blood cell count or cholesterol level. The second part of the FDA's definition is a response to exposure or intervention, which essentially means that we can use this biomarker to characterize the state of your health. We can say, for example, that low red blood cell count in the blood might indicate anemia. In short, a biomarker is any biological measurement we can take to accurately measure the state of disease. In a medical setting, they can replace symptoms such as weakness or nausea as the marker for disease, because those are rather subjective, while biomarkers are ideally more concrete. Biomarkers allow us to glimpse inside the body that we just can't get by looking at a patient and asking them how they feel. So obviously biomarkers are crucial for diagnosing disease, but biomarkers are also crucial for drug development, and that's really what we're here to talk about today. Scientists can rely on biomarkers because most of the times they aren't working on humans, they're working on mice or rats or even monkeys. You can't ask an animal when's the first time they started experiencing symptoms like you might with humans because they won't respond. So scientists have to rely on biomarkers to tell them when the pathology is beginning or ending in an animal. Take, for example, alpha-synuclein for Parkinson's disease. In a research setting for Parkinson's, you might get a sample of cerebrospinal fluid, or CSF, from an animal and test for the presence of a molecule called alpha-synuclein, or alpha-syn. Alpha-syn is the main component of Lewy bodies, which is basically the toxic buildup that happens in your brain during Parkinson's. So you can take a sample of CSF to ensure that you have elevated alpha-syn levels. This ensures that the animal is actually experiencing Parkinson's. Then you can treat that animal with a potential drug and see if subsequently the alpha-syn levels have gone back down. This type of thing happens in all forms of research, from experiments that happen in a petri dish to ones that happen in animals, and it's essential for determining that A, the subject is actually experiencing some form of disease, and B, that your drug impacts that disease via how it impacts the biomarkers. Every disease state has a multitude of biomarkers, and many of them are still undiscovered. And that's the job of scientists, is to find the biomarkers that represent the disease and then to find treatments that then change those biomarkers. In later stages of drug development, the FDA also relies heavily on biomarkers to tell when a drug is working or the drug's efficacy. If they want to approve of a new drug, let's say for heart disease, they require a myriad of evidence, but one of the main evidence that they'll use is biomarkers. They might consider blood pressure, for example, as a biomarker to show that the drug is working. They will also use safety biomarkers such as creatinine in the blood to show that the drug is not affecting normal function of the kidney. In the case of creatinine, they would want to see that the biomarker does not change when exposed to the new drug. Now, the FDA requires a lot of evidence to show that a biomarker is actually measuring what we say it's measuring. While blood pressure is pretty self-evident why it's a good biomarker for heart disease, other biomarkers are not as clear. Scientists have to prove to the FDA that their random molecule in the blood is not only correlated in the disease, but a predictor of the disease, that this molecule will increase and decrease as the disease gets worse or better. As you can imagine, this is not an easy task to prove, but it happens all the time, and we're constantly exploring new biomarkers that can give us deeper and more accurate measurements of disease. Biomarkers themselves can even go through their own approval process where the FDA will determine the validity of a certain biomarker before deciding to use it as evidence in later clinical trials. Biomarkers are the backbone of modern drug development and medicine. They are crucial for every stage of research, from research to development to diagnosis. Okay, so that was a pretty deep dive on the importance of biomarkers. Now let's talk about this new and highly anticipated biomarker, neurofilament light, or NfL. I say new not because we just discovered it, we've actually known about it for quite a long time, but because we're using it in new contexts to do new things. This new context is its involvement in a clinical trial for ALS. I'm going to talk about the whole clinical trial in a little bit because it's actually quite interesting. I tuned into a little bit of the live discussion the FDA had about it, and despite being way too many hours long with no pictures or font changes in any of their PowerPoints, it was actually quite interesting. But at the end of the trial, FDA accepted the use of NfL as a biomarker to approximate the state of ALS. But before I talk about all that, what is NfL? NfL is the National Football League, and it's a collection of American football. No, I'm just kidding. NfL actually stands for neurofilament light. It's a broken down form of a molecule called neurofilament, which is found all over neurons. There are several types of neurofilaments, but they all work to add structure to the axons of the neurons. They also help to ensure fast signal propagation down the axon, mainly of myelinated neurons. Now, when a neuron experiences an injury to its axon, these neurofilaments will break down and exit the brain. They're broken down into various shapes and forms, such as neurofilament heavy and neurofilament medium. These are pretty self-explanatory about their shape. One is larger, one is medium, and neurofilament light is the smallest. Neurofilament light is the most common form, and it will leave the brain to enter circulation where we can easily test for it. This is one of the reasons why NfL is so highly favored for neuroscientists. It's invasive and dangerous to take samples from the brain or CSF, cerebrospinal fluid. So having a biomarker that exists in the blood that allows us to look at the brain is a non-invasive and safer way to look at the brain. I say blood, NfL actually exists in plasma, which is a subcategory of blood, but for the sake of simplicity, I'll just use blood in most of this video. So NfL is a measure of axonal injury. Increased blood NfL means more injury in the brain. This is the case for ALS and many other neurodegenerative diseases such as Alzheimer's, Parkinson's, multiple sclerosis, and frontotemporal dementia, and Huntington's. In any neurodegenerative diseases where axonal degradation is a key symptom, NfL can potentially be used to measure progression of the disease. In fact, NfL can go even further. It can indicate disease before you even start experiencing symptoms. In diseases like ALS and MS, NfL starts to accumulate in the blood before symptoms become visible to the patient or doctors. Blood NfL will then continue to increase as the disease gets worse. Over the past couple decades, scientists have been hard at work characterizing these changes in NfL, characterizing what blood levels of NfL correlate to which stage of disease and how this changes from disease to disease. But in general, for all neurodegenerative diseases, the more NfL you have in your blood, the worse the disease. Because of this, via simple blood test, we can see how far along you might be in a disease, even catch the disease before symptoms starts, or develop new drugs. NfL is the measurable breakdown of neurons. It's pretty versatile, and there's potential to use it in practically any neurodegenerative diseases. But up until now, we really haven't. The approval process for most neurodegenerative drugs relies on symptomatic evidence such as cognitive decline or genetic factors via RNA screenings. NfL really hasn't been used by the FDA to grant approval of new drugs, or rather, they won't count it as sufficient evidence. It has to be alongside a myriad of other evidence. So it's never been the principal indicator of disease and subsequent reversal of that disease until now. Last year in 2023, the FDA used NfL as key evidence to get the new ALS drug called Tofersen accelerated approval. Basically, the FDA gave its official seal of approval to NfL as a biomarker for ALS. Here's how it happened. Now, if you don't know, ALS is a type of neurodegenerative disease which causes the neurons that innervate muscles to die. As this happens over time, patients lose function in their extremities, moving up their limbs towards the brain until function of the heart and lungs is lost. There are different forms of ALS, and so each form needs sort of a unique treatment. So Tofersen is designed specifically for a type of ALS called SOD1 ALS. In SOD1 ALS, the SOD1 gene has a toxic gain-of-function mutation, meaning it used to work, but now it started doing something bad to the neurons. This is like if a robot that normally functions to clean suddenly started breaking things instead of cleaning. So it gained a toxic function. The goal then of Tofersen is to reduce the expression of this toxic gain-of-function SOD1, which should prevent ALS from getting worse. In the clinical trial, 108 patients were treated with either the drug or the placebo. Each patient received 8 injections into their spinal cord over the course of 24 weeks and then were assessed for improvement. Now, statistically, they did something that I think is pretty interesting and adds to the validity and reliability of their data, which is that they used what I'm going to call canaries in the cave. Of their 108 patients, 60 of them had a faster progressing form of ALS. Any symptomatic changes would be more extreme in these faster progressing subgroup than a slower progressing subgroup. So changes that we saw in the faster group would mean that there's potential to have changes in the slower group, but if there was no changes in the fast group, there's no way there would be changes in the slow group. Symptomatic changes were measured via ALS FRSR score, which is essentially a measure of functional deterioration and motor impairment. So instead of looking for ALS FRSR between all treatment groups and all placebo groups, they only look for changes between the faster progressing treatment group and the faster progressing placebo group. In this trial, the faster progressing subgroup, which should have shown more extreme differences, didn't show any differences between placebo and treatment. Because of this, the researchers didn't even need to look at the slow progressing group. Any changes in the slower group would have been due to statistical anomalies, not real change. Their canaries didn't show change, so no one showed change. Now, wait a minute. This is weird. This new drug, Tofersen, which has already been approved by the FDA, did not show conclusive changes in symptoms in a clinical trial. With a p-value of 0.97, they showed absolutely no functional change between placebo and drug. But, and this is why it got approved nonetheless, it showed dramatic decrease to 2 biomarkers. And I mean dramatic. The 2 biomarkers in question are 1, our favorite NfL, and 2, the toxic SOD1 protein that is thought to cause SOD1 ALS. Both of these biomarkers decreased so much so to convince the FDA to approve despite no symptomatic changes in this first trial. Patients receiving the drug experience a reduction in SOD1 in their cerebrospinal fluid or CSF by 29%. Placebo patients actually increased their SOD1 by 16%. And that was in the fast progressing group. In the slow progressing group, it was decreased by a whopping 40%. If SOD1, the genetic mutation associated with the disease, is genuinely the cause of the disease like we think it is, then that means we are going straight to the source of the cause of the disease and dramatically reducing it. For NfL, the numbers are even more convincing. Plasma NfL decreased by 60% in the fast progressing group, while the placebo group experienced an increase by 20%. For those of you who aren't particularly familiar with statistics in biology, that amount of change is insane and rarely seen in new drugs. So, despite not really showing any difference in physical symptoms, the molecular biology of it all is telling us that this drug is really working. There's sort of this hope that maybe if the drug is given early enough in the progression of the disease, we can prevent the disease altogether. I mean, the biomarkers are saying it should be possible. So, due to the convincing evidence from SOD1 and NfL changes, the researchers decided to continue the trial past its expiration date, basically giving all patients, both those who originally received placebo and those who received treatment, the opportunity to switch to the drug and take it for another 52 weeks. This is called an open label trial because now we know that everybody is on the drug. There's no placebo group anymore, just those same patients from earlier seeing what happens when you take the drug for longer than 24 weeks. In this open label trial, 88% of patients from the original trial decided to either continue taking Tofersen or switch from placebo to Tofersen for a subsequent 52 weeks. That is quite a lot of patients deciding to continue, which could have been due to a lot of things, including the unfortunate fact that people with SOD1 ALS don't really have a lot of other options, but it also demonstrates that the patients believe the potential aid outweighs any of the side effects. So during this extended trial, there was a little bit more success. People who had been taking the drug all along sort of leveled out in both of their NfL and SOD1 levels. Basically, they maintained low levels for the continuation of the trial, which is really good. Sometimes it'll go back after taking the drug for a while. Meanwhile, the placebo group, which had just switched to the drug, immediately started to experience reduction in both SOD1 and NfL. By 52 weeks, the late start group had biomarker levels that came close to matching what the early start patients were at. This data is genuinely so clean. To show that immediately after switching from placebo to drug there's a change, shows that the changes are really due to your drug and not due to something like the treatment effect, which is a phenomenon where the act of receiving treatment alone causes changes, not the actual drug. Also, the data is highly correlated across time, with more decreases happening as more time passes, so it's just fantastically clean. Again, the biomarkers are showing convincing and clean data. But more interesting, let's look at the clinical symptoms. Measured again via their ALS-FRSR score, patients who started the drug earlier appear to experience a slower decline than patients who started late. There's no placebo group to compare to, but this hints at the possibility that starting the drug early might genuinely help progression of the disease. And showing this is really the point of this trial, to show that early start prevents progression. So with this and a package of other evidence that I haven't talked about, the FDA gave accelerated approval to Tofersen. Meanwhile, the researchers have started a new clinical trial post-approval to look for further evidence that early start prevents progression. In this post-approval trial, researchers are now giving the drug to patients who have the SOD1 mutation but no symptoms yet. The hope is that Tofersen can delay the start of ALS or even slow its decline by modifying SOD1 levels before it has the chance to cause damage. This trial is predicted to wrap up in 2027, but regardless of this trial, the drug is already approved for patients. And it was approved not for its effect on clinical symptoms, but for its effect on biomarkers, specifically NfL. This is the first time that a blood biomarker has been used to gain accelerated approval in a neurological therapy. And as a researcher and an advocate for patients, this makes me ecstatic. Not only were they able to use this evidence to approve the drug way faster than they would have if they had waited to see clinical trials, but we've improved the lives of patients. Instead of taking a spinal tap, they can give a blood sample, something that everyone has done. With NfL being used in this context, we can more confidently move forward using it for drug development process. But as excited as I am to see this biomarker being taken so seriously, I do want to add a word of caution to the use of biomarkers in general. While biomarkers are huge for diagnosis and treatment, they aren't a disease. They are markers for the disease. As much as we can say that NfL decreases are good, they don't mean anything if the experience of the patient is not changed. As scientists, we need to be ever cautious of this fact and constantly reevaluate the validity of our biomarkers, even after they've been used by the FDA. I think a really good example of biomarker reevaluation is seen in prostate cancer. For a long time, the biomarker prostate-specific antigen, or PSA, was used to indicate prostate cancer. Doctors would do a blood screening for PSA levels and use this to determine if you likely have cancer. Patients with elevated blood PSA would then go on to do more invasive screenings, biopsies, and even receive surgery. However, we learned over time that high blood PSA doesn't necessarily mean you have prostate cancer. Men can have elevated blood PSA without having prostate cancer. So for many years, men were undergoing unnecessary biopsies and even treatment because the biomarker PSA was giving us false positives. As this became clear that we were overdiagnosing patients, guidelines on using PSA for diagnosis has been modified to prevent unnecessary treatment. So it's important to make these reevaluations for all drugs and all biomarkers as more evidence becomes clear so that we can constantly be improving medicine. Similarly, reevaluation does and should happen in drug development. For example, historically, we have used a biomarker called total tau to measure Alzheimer's. It increases in Alzheimer's, but in modern research, total tau is not really used for Alzheimer's anymore. Total tau is not specific to Alzheimer's. It occurs in other neurological diseases. So you can't have full confidence that when you see an increase in total tau, you're actually seeing Alzheimer's. But we didn't throw total tau away altogether. Instead, we reevaluated its non-specificity and got more specific with it. When looking at Alzheimer's, we now measure a more specific form of tau called phosphorylated tau or phosphotau. We use phosphotau in combination with other biomarkers to evaluate AD, and this gives us a more accurate picture of what's happening than if we were to just use total tau. While it's good to use total tau when that's all we had, we've made improvements to that, and now we have a more complete picture. I hope it's clear that I'm not saying biomarkers can't be trusted. I believe scientists work in good faith with as much evidence as they have available, but when more evidence becomes available, it's crucial to integrate that new evidence into our old understandings and potentially modify what we thought we knew. This is how science works. It's iterative and we never have the full answer. There's always more to be discovered. There's always room to question further, and that skepticism and drive to improve science is really my favorite part. I hope that in 20 years or so, when we are using NfL confidently as a biomarker for multiple neurodegenerative diseases, including diagnosis, there are still people asking themselves, how valid is this biomarker? Is it actually showing disease, or could there be a better and more specific biomarker to replace it? But what do you guys think? Are you convinced by the biomarker evidence, or do you think we need more evidence? Is there a biomarker with controversy that you know of that I didn't talk about? Rant about it in the comments. I genuinely love reading anything you guys have to say. I'm a very small channel, but I put a lot of work into making these videos as accurate as possible. So thank you for watching what is probably one of my longer videos, and please subscribe so I can see you in the next one.